classroom. This is Mr. Wong speaking here. We're going to go through a past paper question for what is this? Module 5 of Inquiry 1 of Physics Year 12, which is on projectile motion. This is 2004 and question 16. So we have a projectile that is fired at a velocity of 50 meters at an angle of 30 degrees to the horizontal. The question is asking us to determine the range of the projectile, which is, I just write down as Sx. Now, for those who aren't quite sure what this question is trying to portray here, let me try and draw a diagram like this. So imagine we have like a little cannon, okay, and we have our ground, and we fire this object or projectile out. This 30 degrees to the horizontal is from this horizontal plane here going up by 30 degrees, sorry. So that's what we mean by 30 degrees to the horizontal. This 50 meters per second refers to this mark here. Now, as you can see, we have a sort of diagonal motion. And what you would have learned back in year 11 is if we have a resultant vector, which is pretty much what this looks like, it will have a horizontal and vertical component. So meaning by as this ball goes out, it's going to be moving like so, and obviously as it's rising, it's moving up like that as well. We know that for the component of Ux, because there's no air resistance, there is also not going to be any, how to put it, changes in its velocity, while as the vertical component will change, okay? Now, let's just have a look at how we can find the range. To find the range, we're going to use the following kinematics equation, uxt plus half axt squared. Remember what I said before, that because there's no air resistance, or at least the questions we talk about don't involve air resistance, acceleration in the x component is 0. And so we have Sx equals to the following like so. So the question is now, what is Ux? And also, what is T? Now, I want everyone to remember this. Ux is relatively easy to recall. So if I draw the triangle out here, we have 30 degrees here, 50 meters here, and we want to find this component. If you recall your trigonometry, this is a cosine relationship because we have the adjacent side here and the hypotenuse. So in order to find it, it would simply be our resultant vector multiplied by cos 30, okay? So that's relatively straightforward. Time, on the other hand, you need to remember one thing. The time it takes for something to fall is completely dependent on the y component. Okay, so if I throw a ball in the air, or if I, peg a ball from one side of the room to another side, it is the y motion that actually determines how long it takes for the ball to drop. Okay, so what we're going to assume is we have our projectile, we launch it, and it will have a uy component. At peak height, the velocity is 0, and when it hits the ground, it also is 0. Now, because it is being fired at the same position as it lands, the total time that we have here, time total, and the time it takes to reach the peak height is just a difference of a half, or a half of each other, right? So the time it takes for us to reach the peak height here is half the time it takes to reach to the final destination. So let's use this formula. Vy equals to uy plus ayt. We're going to say that Vy is 0 because we're reaching peak height. We know that Uy is 50 sine 30, which is actually 25 meters per second. So 25 here. Ay represents the acceleration of gravity, and that's negative 9.8 because we're saying that going down is the negative direction. Okay, So if I rearrange that around, okay, I get that my time is approximately 2.551. Okay, now this is just for the sake of calculation. You should try and round off at the very end of the calculation. So that's the total trip time to reach the peak height here. Okay, so that's for peak height. If I want to find the total time, maybe I'll do time half. If I want to find the total time, times that by 2, and I find that it's approximately 5.102 seconds. So that's the total trip time. Okay, now that I know my total time of that projectile's motion, I can now substitute this in to find the overall displacement. So ux, we said, was 50 cos 30. So let's see if that's a nice round number we can use. And if not, we can just use 50 cos 30. Okay, so it is 43.3. We'll use 4 sig figs like I did before. Multiply by our time of 5.102. And I find that the approximate range in this context here is 220.9 meters in length. And that's how you solve this problem. So just remember one thing. Although we're trying to find the range in this question here, if we don't know the time, we actually need to solve in the y component to find time first before we can find the actual range. So how far an object travels for a projectile in this context here depends on the time, and the time it takes for it to fall is dependent on the vertical motion. If you found this video useful, please like and subscribe, and I'll see you next time.